We will now study what is perhaps the most important class of functions in real analysis, namely continuous functions. We will first understand intuitively what continuous functions should be and then move to a rigorous definition. First, let us revisit some of the definitions given by people in the past. Newton and Leibniz had defined a continuous process as a process that does not have gaps. What do you mean by a function not having gaps? That's something that's not very clear. However, notice that a function and its graph are kind of one and the same. Hence, what one can define is that, this is the definition given by Euler, function is said to be continuous if its graph is a curve described by a freely moving hand. Now that is a little ambiguous language for a modern reader. So how you should interpret is that you can draw the graph without lifting your hand from the paper. Notice that the definition by Newton and Leibniz is not exactly same as the definition given by Euler. Euler has added a new concept, namely he has used the metaphor of motion, which is a new concept. So this will change some of the things. So let's just keep in mind that there is something different between the two. We will see the difference more clearly when we go to an example. The guiding example that one should keep in mind is that of the following function, which takes the value -1 if x is less than 0 and +1 if x is greater than 0. To emphasize that the function takes value 1 at 0, I will darken the point 0, 1 and I will put a circle around 0, -1. It is plainly obvious that this function is discontinuous with respect to Newton and Leibniz's definition. However, I claim that it is not as simple to see that this function is discontinuous with respect to Euler's definition. Of course, if you start from a point on the left hand side and go towards the right hand side, then as soon as you reach 0, I will be forced to lift my hand and keep it here. Similarly, if I started from a point on the right hand side of 0, and then I continue drawing towards the left hand direction, then as soon as I reach this point, I will be forced to lift my pen and then continue drawing here. However, if I start from a point on the right hand side of 0 and continue drawing towards the right hand direction of that point, then I can keep drawing till as much time as I want. Similarly, if I start drawing from a point on the left hand side of 0 and continue drawing towards the left hand direction, then I can again keep drawing for as much time as you want. At this point, some people may complain that if I start from the right hand side of 0 and continue drawing to eternity to the right hand direction, then I am not tracing the entire function by doing this. But that is the case even for better functions. Namely, if you look at the function f of x equal to constant 1. It's a constant function. So clearly this should be continuous. Whatever notion of continuity you come up with, this function has to be continuous. But even for this function, suppose I start drawing from the value at 0, that means I start from here and I keep drawing towards the right hand direction, then I will never trace the values of the function for x less than 0. So this is something that is inherently true. That is because the domain which is real set of real numbers is infinite, is the reason why you can never draw the graph of the entire function. So perhaps what Euler means is that irrespective of the starting point or starting direction, we should be able to draw the graph without lifting hand for as long as one wants. Because otherwise we can have worse functions which will have exactly one problematic point. Let us look at one such example. So let us look at the function that takes the value 1 by x if x is not equal to 0 and 0 if x is equal to 0. So the graph of this function will look something like this. See, the value at 0 is not really important. I could have given any function, any value at that point, but I just chose 0 for concreteness. That's all. So if you look at any point other than 0 and start from the 0 comma f of x comma f of x, then I can draw towards the left hand direction or right hand direction for as long as I want. However, if I start from 0, then I would not know how to proceed. So there is exactly one starting point which is problematic. So Euler's definition should be that there is no such starting point. There are some important questions that we need to address at this point. Is this definition precise, or is it a definition? It will not be a definition if there exist functions for which we cannot check whether they satisfy Euler's condition or not. As far as I can see, we can check Euler's condition for every function. If you know of some function for which Euler's condition cannot be verified, or if you can come up with such a function, please let me know. Another important question is this a good definition of continuity? We will see some reasons why this is not good enough for our purposes, but before that we will take a slight detour and we will look at another possible definition of continuous functions. In fact, this was a definition which was used by some people. Let f be a function from R to R, and let A and B be 2 points on the real line. I am assuming without loss of generality that A is less than B. And I am looking at the values of the function at A and at B. I am drawing it in such a way that f of A is less than f of B, but similar kind of picture will hold for f of the other case also. So this is the point A comma f of A, and this is the point B comma f of B. Now what you are doing is you take a point which is in between f of A and f of B, and let's draw the line parallel to the x-axis passing through this point. Okay, it looks something like this. Now if you want to go from f of A to from this point, that means A comma f of A to B comma f of B, then we intuitively feel that if we draw a path from A comma f of A to B comma f of B without lifting the pen, then it has to intersect the red line at some point or the other. That means whatever value you take between f of A and f of B, there exists some point C such that the f of C is that value. Okay, so if you take a y which is less than f of B and which is greater than f of A, there exists a C belonging to A comma B such that f of C is equal to 1. Okay, and this property is called as the intermediate value property. We will often abbreviate this as IVP. Thus, it seems intuitively clear that if a function satisfies Euler's definition of continuity, then it satisfies IVP. In fact, a lot of people believed that the two are equivalent. However, later it was shown by Darboux that that is not the case. Darboux proved much stronger result than what I am going to discuss right now. But even what the simplified form that I am going to talk now is quite interesting. In fact, Darboux's example illustrates that IVP is not a good definition for continuity. Let us see what this example is. The function of interest is f of x is equal to sine 1 by x if x is not equal to 0 and c if x is equal to 0. So how does this function, the graph of the function, look like? What happens is that as the function gets closer and closer to 0, the oscillations of this function gets faster and faster. And at 0 we cannot really define a value, so that's why at 0 we define the function separately. So the graph has some structure like this. It's oscillating, but the frequency is increasing, so it's even smaller. I'm not very good at drawing these kind of things, but the amplitude is same, but the frequency is increasing. So that's what it means. Okay, and similarly from here also you have the same kind of picture. The amplitude is same, but the frequency is increasing. Okay, and at 0 we can define it any value c. Again here what we are doing is we are taking c is in 0, 1. Okay, so please observe this. Now notice there are three possibilities. One case is both a and b are less than 0. That means it's something of the form where a and b are like this. Okay, that is one possibility. Or you can have a and b like this, where both a and b are greater than 0. Or you can have a third possibility where a is less than 0 and b is greater than 0. These are the three possibilities in which you can have the 2 points a and b. Intuitively, if at all there is a point, if at all there is a problem, the problem is near 0. So if we take the 2 red points or the 2 green points, then we should not be in trouble. On the other hand, if we take the 2 yellow points, that means if we take a to be less than 0 and b to be greater than 0, then what happens? Then it contains 0. But near 0, it takes all values between -1 and +1. Hence, the function trivially satisfies intermediate value property. So as the intermediate value property should be satisfied for all the different possibilities of a and b, the function should satisfy intermediate value property. But notice that this is problematic for two reasons. First of all, whether this function satisfies intermediate value property or not did not depend on the value of the function at c, and that is kind of paradoxical. Okay. On the other hand, this is also problematic for a different reason. See, the thing is, if you started from the point 0, f of 0, then you cannot continue the graph without lifting your pen. Hence, this does not satisfy Euler's condition. So, Euler's condition and IVP are certainly different from each other. And in some sense, this paradoxical result tells us that IVP is perhaps not the right definition for continuity. So let's stick with our definition of Euler's condition to be the definition of continuity for the moment. But we will see next that even that has some issues. Let's get to that now. Now the important thing to notice is that we were not just interested in functions f from R to R, but we were also interested in functions f from A to R, where A is some subset of R. Now if you look at the function f from say 0, 1 union 2, 3 to R, given by f of x is equal to 1. Okay. Do you think this function is continuous or not? Ideally, you would want this function to be continuous because it's a constant function. If constant function is not continuous, then what else can be continuous? But if you look at the graph of this function, so let's draw the graph of this function. Let's say this is 0, this is 1, this is 2, and this is 3. Thus, the graph of the function would look like this, which clearly cannot be drawn without lifting the pen. Hence, this function does not satisfy Euler's condition of continuity. But one might say that that is because there is a gap in the set, and that is the reason why there is a gap in the graph. So perhaps what you want is something which is a little bit modified. You might have to say that if suppose your domain is in some sense drawable without lifting your hand, then the graph should also be drawable without lifting your hand. Okay? Or in other sense, if the domain does not have gaps, then the graph should also not have gaps. Now we can make these things precise. For example, we can rigorously define what one means by a gapless set. However, that is beyond the scope of this video or this course. They belong to a subject called topology. It so happens that if you are interested only in functions from the real line to real line, then the property that gapless sets are taken to gapless sets is equivalent to the intermediate value property. More precisely, the only gapless sets on the real line are intervals. Notice, however, that even though this function that we just defined does not satisfy Euler's condition, it satisfies intermediate value property. So does that mean in some sense intermediate value property is better suited, because after all we wanted this function to be continuous? Not really. This just so happened that this function is special. We can similarly construct functions for which the intermediate value property is also violated. To illustrate this, we will consider another function on the same set. So let's call this function g. So let g be a function from 0, 1 union to 3 to r, and let g of x be equal to x. Again, this is 0, this is 1, this is 2, and this is 3. So the graph of the function looks like this and this. Clearly, this function does not satisfy the intermediate value property. If you take a and b to be, so if you take this to be a and this to be b, okay, then this is f of a, this is f of b, and if you take a value c like this, then there is no value, then there is no point between a and b such that that value is attained. So this violates intermediate value property. Just to illustrate that these gaps can be even more complicated, let us look at a third example of a function that violates intermediate value property and Euler's condition. But ideally it should not. So let us look at the function f from q to r such that f of x equal to x. Here again, the intermediate value property is violated. Because why? Because given any two rational numbers, you have an irrational number in between. So there is a gap in some sense. And for the same reason, you cannot really draw the graph, because you will have to jump, because you are supposed to plot only the value of the function at rational points. And that you cannot really do without lifting your hands. So it violates both Euler's condition and the intermediate value property. And this is just the beginning of the story. We can get even more complicated and complicated sets that has gaps in it. But as I said before, that is all beyond the scope of this course. So now that we have agreed that Euler's definition is not sufficient for our purposes, because we are interested in functions f from a to r, let us revisit our motivating examples and see how else we can define continuity. In order to do this, let us just give some names for these two functions. Let's call this function f of x, which is the function that takes the value 1 if x is greater than or equal to 0 and minus 1 if x is less than 0. And this is the function g of x, let's call it a different name, which is equal to 1 by x if x is not equal to 0 and 0 if x is equal to 0. Even though both these graphs were impossible to draw without lifting the hand, there were some subtle differences. For example, the only problematic point for g of x was 0. If you start from g of x, then you do not know how to continue drawing the graph without lifting your hand. But on the other hand, if you take any other point, you can keep drawing the graph of the function till eternity, and you will never have to lift your hand. On the other hand, for f of x, if you take any point, let's say a point towards the left hand side of 0, then if you go to the left hand side, then you can keep drawing for eternity. But if you go to the right hand side, then you will eventually have a problem. Similarly, if you take a point to the right hand side of 0, then you can go to right hand side for eternity. But if you go to the left hand side, then as you reach 0, you will be forced to lift your hand. So we have noticed that we have to lift the pen precisely when we reach 0. So instead of starting from a point and going all the way towards the right hand direction or left hand direction, let's say that as soon as we pick a point, the direction is fixed. The direction is the direction towards 0. So if the point is towards the left of 0, then the direction is right, and if the point is towards the right hand side of 0, then the direction is left. So, and what you do, you start from that point and go till x equal to 0. You do not go any further. Okay, so if you do that, and if you take a point A like the green dot, then you look at the point a comma f of a, and then you continue along the graph till you reach x equal to 0. As soon as you reach x equal to 0, you have to jump and take the value this. On the other hand, if you had started from a towards the right hand side and look at the a comma f of a, and then if you keep going till 0, you do not have to lift your hand at all. So perhaps the problem was that the value of f as x approaches 0 from the left is different from the value of f at 0. We had already seen how to capture the value of f as x tends to 0 from the left as limit x tends to minus infinity f of 1 by x. We had seen that this is the value of f as x approaches 0 from the left hand side. We will introduce a notation limit x tends to 0 minus f of x to mean that it is the limit of f of x as x approaches 0 from the left hand side. And we saw that in this case the problem is that this is not equal to the value of f at 0. And that is kind of the problem. Let us repeat. We saw that f is continuous implies that limit x tends to 0 minus f of x is equal to f of 0. But what is so special about 0? 0 is special for the function that we saw earlier, but it's not special in general. Like, for example, if suppose you had a different function that takes the value minus 1 till 1, x equal to 1, and at 1 it takes the value 1, and then it keeps taking the value 1 after that. Let me again put a circle here to show that that is not taken here. That value is not taken. Now for this function, the value of f of x as x tends to 0 from the left is equal to the value of f at 0. Correct? But the problem is the value of f as x tends to 1 from the left is different from the value of f at 1. Although we had not seen the precise definition of the value of f as x tends to a from the left for a general a, we had kind of implicitly seen that. Let us now rigorously define what it is. So limit x tends to a from the left hand side of f of x is nothing but limit x tends to minus infinity of f of 1 by x plus a. So this is how I define. And as you can clearly see that this will, as x tends to minus infinity, this will get closer and closer to a, and for each value 1 by x is negative, so a plus 1 by x is less than a. So it is approaching a from the left hand side. And similarly, we will define the limit of f as x tends to a from the right hand side as limit x tends to infinity f of 1 by x plus a. Here again, as x tends to infinity, 1 by x tends to 0, and a plus 1 by x is always greater than a, as 1 by x is positive. So this is how we define the value of f as x approaches a from the left hand side and from the right hand side. And we saw that if f is continuous at all points, then this implies that limit x tends to a minus of f of x is equal to f of a for all a. Again, if we look at a different example, so in this earlier example, how did we define the function? The value was -1 till 0 and 1 at 0. But now we will take the value at 0, we will give the value -1. And for all values greater than 0, I take the value +1. For this function, limit x tends to 0 minus f of x is equal to f of 0. But on the other hand, limit x tends to 0 plus of f of x is not equal to f of 0. And even this function fails to be continuous. So it is not enough that limit x tends to a from the left of f of x equal to f of a. It is also important that limit x tends to a from the right of f of x is equal to f of a for all a. So both these conditions should be satisfied for a function to be continuous. More precisely, if we do not want the step functions to be continuous, then we should enforce that continuous function should have these two conditions. The idea is to use this condition as the definition of continuity. More precisely, we say f is continuous if and only if limit x tends to a minus f of x is equal to f of a is equal to limit x tends to a plus f of x. However, there is a small problem with this definition which we will see next. Suppose our a was equal to 0, 1 union singleton set 2. Okay, and if you are looking at a function f from 0, 1 union singleton set 2 to R. Now, you cannot define limit x tends to 2 minus f of x or limit x tends to 2 plus f of x. So what can we do in such a case? The problem here is that 2 is not a cluster point of A. Which is equal to 0, 1 union 2. Also notice that the property limit x tends to c minus f of x is equal to f of c is equal to limit x tends to c plus f of x is a property that is inherently tied with the point c. So why should we define continuity as a global property? Instead, what we can do is we can define continuity as a property at c. Okay, so we define a function to be continuous at c if this condition is satisfied, and we say a function is continuous if it's continuous at every point in its domain. So let us define a continuous function as, we say a function f from a to r is continuous at a if a is not a cluster point or if a is a cluster point and limit x tends to c to a minus f of x is equal to f of a is equal to limit x tends to a plus f of x. So if either of this condition is satisfied, then we say that the function is continuous at a. Finally, we say that a function f from a to r is continuous if f is continuous at all A in A. Notice that we are still using the motion metaphor that was there in Euler's definition. However, we have made some changes. In Euler's definition, we started from a point and moved away in one of the directions and checked whether we have to lift our hands at some point. Here we are doing the opposite. We are moving towards the point. That means we are approaching the point from one of the directions and checks what happens to the value of the function as x approaches this value. So they are similar yet different, and I want you to note the difference. Just to stress that the left hand limit and right hand limit need not be as simple geometrically as in the examples that we saw, I want to give you another example. Let us define f of x equal to x if x is a rational number and 0 otherwise. I want you to prove that limit x tends to 0 minus of f of x is equal to f of 0 is equal to limit x tends to 0 plus of f of x. I want you to do this as a homework. And this homework would imply that f is continuous at 0. Notice, however, f cannot be drawn even in a neighborhood of 0 without lifting hand, of course. So in some sense, we have really moved away from Euler's definition. Notice that in the second lecture on limits, we had shown that limit x tends to minus infinity f of 1 by x is equal to L is equivalent to, for every epsilon greater than 0, there exists an n of epsilon such that mod of f of y minus L is less than epsilon for all y such that 0 is greater than y is greater than minus 1 by n of epsilon. And we had defined this n of epsilon to be delta. 1 minus 1 by n of epsilon as delta of epsilon. Okay, so this whole thing we can rewrite as, for every epsilon there exists a delta that depends on epsilon such that 0 is greater than y is greater than minus delta implies that mod of f of y minus L is less than epsilon. So you could have rewritten like this. Similarly, you can write that limit x tends to infinity f of 1 by x is equal to L if and only if for every epsilon there exists a delta of epsilon such that 0 is less than y is less than delta implies that mod of f of y minus let me rub that, minus L is less than epsilon. And in this video we had given some convenient names for this. We called it limit x tends to 0 minus of f of x, and this as limit x tends to 0 plus of f of x. And what have we done in this relationship? See, limit x tends to minus infinity f of 1 by x is a notion of it approaching 0. That means x is approaching 0, and what happens to the value of f of x as x approaches 0. On the other hand, when we say 0 is greater than y is greater than minus delta, what we mean is that y is close to 0. Similarly, 0 is less than y is less than delta means that y is close to 0. So we have related the notion of approaching 0 with that of being close to 0. So what we are doing is that we are connecting the metaphor of motion with the metaphor of proximity. So, and this way we are relating the two notions. Finally, we will show that similar results holds also for limit x tends to a minus f of x and limit x tends to a plus of f of x. More precisely, we say limit x tends to a minus f of x is equal to L if and only if for every epsilon greater than 0 there exists a delta such that 0 is greater than y minus a is greater than minus delta, implies that mod of f of y minus L is less than epsilon, and limit x tends to a plus f of x equal to L if and only if for every epsilon greater than 0 there exists a delta, and this delta depends on epsilon in both the cases, such that 0 is less than y minus a is less than delta, implies that mod of f of x minus L is less than epsilon. The proof of this is very similar to what we did earlier, so I leave the proof of these two claims as a homework. At this point, let us observe one more thing. How did we define limit x tends to a of f of x is equal to L? We said that this is true if and only if for every epsilon greater than 0 there exists a delta that depends on epsilon such that 0 is less than mod of x minus a is less than delta, implies that mod of f of x minus L is less than epsilon. However, this is equivalent to for every epsilon greater than 0 there exists a delta that depends on epsilon such that 0 is less than x minus a is less than delta, implies that mod of f of x minus L is less than epsilon, and both should be true. That's what I mentioned by and. For every epsilon greater than 0 there exists a delta of epsilon such that 0 is greater than x minus a is greater than minus delta, implies that mod of f of x minus L is less than epsilon, which we saw is equivalent to limit x tends to a minus f of x is equal to L and limit x tends to a plus of f of x is equal to L. Thus, we can rewrite the definition of continuity as follows. We say f from a to r is continuous at a belonging to a if either a is not a cluster point or if A is a cluster point and limit x tends to a f of x is equal to f of a. That means if we wanted, we could completely do away with the metaphor of motion from the definition of continuity. Let us rewrite definition in terms of epsilon and delta. That is in terms of proximity. Definition. Let f from a to r be a function and a belongs to a. We say f is continuous at a if for every epsilon greater than 0 there exists a delta that depends on epsilon which is also greater than 0 such that if x is any point such that, notice that here x is not any point in R but it is a point in A. Let me just stress that point. Mod of x minus a is less than delta, then mod of f of x minus f of a is less than epsilon. Notice that we have combined the two conditions that either A is not a cluster point, or if A is a cluster point, then limit extends to A f of x is equal to f of A into one statement. Let us see how this is being done. If A is not a cluster point, then there exists delta such that mod of x minus A is less than delta if and only if x is equal to A. So what you do is you choose this delta for every epsilon. And for this delta, what happens is mod of x minus A is less than delta implies that x is equal to A, which implies that mod of f of x minus f of A is equal to 0, which is less than epsilon. So the function will in fact be continuous at all points that are not cluster points. What about at a cluster point? So at a cluster point, what we have is the following. We have that for every epsilon greater than 0, there exists a delta that depends on epsilon that is greater than 0, such that mod of x minus A is less than delta implies that mod of f of x minus f of A is less than epsilon. This is equivalent to for every epsilon greater than 0, there exists a delta that depends on epsilon, which is also greater than 0, such that 0 is less than mod of x minus A is less than delta implies that mod of f of x minus f of A is less than epsilon, and for every epsilon greater than 0, there exists a delta of epsilon greater than 0 such that 0 is equal to mod of x minus A is less than delta implies that mod of f of x minus f of A is less than epsilon. But here as you can clearly see, the delta does not have any importance. So we could have as well just rubbed these things, okay, which will tell you that for every epsilon greater than 0, 0 is equal to mod of x minus A implies that mod of f of x minus f of A is less than epsilon. But now 0 is equal to mod x minus A can be rewritten as x is equal to A. So for every epsilon greater than 0, x is equal to A implies that mod of f of x minus f of A is less than epsilon. We can rewrite this as follows. But notice that if for every epsilon mod of f of x minus f of A is less than epsilon, then that implies that this is true if and only if x is equal to A implies that f of x is equal to f of A. Why is it true? If a non-negative number is less than every positive number, then it has to be 0. That's the only possibility. Notice that this just means that f of A is equal to f of A, which is a tautology. So we could have actually ignored this whole thing we could have ignored. Okay, and this is equivalent to limit x tends to A f of x is equal to f of A. So if A is a cluster point, then all we have is limit x tends to A f of x is equal to f of A. And hence, this definition matches with our earlier definition. Remember, we had seen in the chapter on limits that limit x tends to C f of x is equal to f of C if and only if for every sequence xn such that xn is not equal to C and xn converges to C, f of xn converges to f of C. On the other hand, if C is not a cluster point then xn converges to C if and only if xn is equal to C for all n greater than some n. For large enough n, xn has to be equal to C. That's the only possibility. Hence, if you are not sure how to see this, prove it. That's a homework. Okay. So because of this, and what happens to f of xn? F of xn is equal to f of c, and that clearly converges to c. So what do we get from this entire discussion? We get from this discussion that we could have defined continuity as follows. We say f is continuous at C if for every sequence xn that converges to C, f of xn converges to f of C. Here again, xn is not just any sequence in R, xn is actually a sequence in A. Let us finally check that our definition behaves well with all the different functions we were interested in. The first function we were interested in was the function that takes -1 if x is less than 0 and +1 if x is greater than or equal to 0. We wanted this function to be discontinuous, and it is indeed discontinuous with respect to our definition. Why? Because limit x tends to 0 minus of f of x is not equal to f of 0. The next function we were interested in was the function that takes values 1 by x if x is not equal to 0, and it takes the value 0 if x is equal to 0. This function is also discontinuous with respect to our definition. Why? Because limit x tends to 0 f of x does not even exist. So it's not true that limit x tends to 0 of f of x is equal to f of 0. Okay, let us write these things. Okay, so here limit x tends to 0 minus f of x is not equal to limit x tends to 0 plus of f of x, and limit x tends to 0 minus of f of x is not equal to f of 0. So this implies that limit x tends to 0 f of x does not exist. Okay, so that was the problem in the first example. In the second example, limit x tends to 0 f of x does not exist. More precisely, limit x tends to 0 minus f of x and limit x tends to 0 plus f of x does not exist. Okay. So, as we wanted, these two functions are not continuous with respect to our definition. Let us directly prove that if f from A to R is the function f of x equal to C for all x, then f is continuous. Why is this function important? This is just a general case of something that we have already seen. We were interested in the function that was defined on 0, 1 union 2, 3 such that it is constant on 0 to 1 and on 2 to 3. We wanted this function to be continuous, but we saw that this was not continuous with respect to Euler's definition. Let us see if this is continuous with respect to our new definition. So we will use the sequential criterion to test this. Let xn be a sequence that converges to C. Then f of xn is equal to C. In fact, whatever the value of x is, f of x is equal to C. So f of xn is also equal to C. And clearly this constant sequence converges to C. So because xn was an arbitrary sequence that converges to C, we can conclude that this function is continuous from the sequential criterion. The next example is the function f from A to R, where f of x is equal to x. Again, the A is arbitrary here. And also, this is a special case of a function that we had seen earlier. See, we were interested in the function that was defined on 0, 1, union 2, 3. Okay, and on this, on 0, 1 and 2, 3, it was defined as f of x was defined as f of x equal to x. So the graph looked like this. Again, we wanted this function to be continuous, but Euler's definition gave that this function is not continuous. Let us see if this function is continuous with respect to our definition. Here again, it is easy to see that f of xn is equal to xn. So if xn converges to c, then f of xn is also converges to c. So because of this, from the sequential criterion, we have that f is continuous. Okay. Finally, using the same thing, we can also prove that if f is a function from a to r, then f of x equal to x squared is continuous. I leave that as a homework. That's all for this lecture. In the next lecture, we will see how we can combine continuous functions to form new continuous functions. Like we can add two continuous functions, we can subtract two continuous functions, we can divide them, we can compose them, etc. That is the content of next lecture. See you next time.